Welcome back to the deep dive. Today, we're going to look at a piece of technology that is probably sitting within a few feet of you right now. It's completely silent, no moving parts, and yet if it stopped doing its job for even 60 seconds, well, the modern world would pretty much grind to a halt.
It's one of those great paradoxes in engineering, isn't it? It's the most passive component in a device, but it's doing arguably the most active work, at least in terms of thermodynamics.
We are talking about the heat sink, specifically aluminium heat sink profiles. And I know on the surface that sounds like we're just talking about, chunks of metal, but looking at the research we've pulled for this, and we're drawing on some really dense technical insights from Eleanor Industries, this isn't just about metal getting hot. This is about the fundamental physical limit of our technology.
It really is. We are hitting what engineers call the thermal wall. We can make chips faster, we can make batteries denser, but if we can't get the heat out, none of it matters. The heat sink is basically the bridge between high-performance computing and a melted paperweight.
So here's the mission for today. We're going to unpack the physics of cooling, what is actually happening at a molecular level when your laptop fan spins up. Then we'll figure out why aluminium is the undisputed king of this space, even over more conductive metals like copper. And then we're going to get into the manufacturing because, frankly, the way they slice and extrude these things it's fascinating.
The techniques are surprisingly violent for something that just sits there looking so static.
I love that description. Okay, let's start with the problem, though. I think everyone listening has had that moment. You're editing a video, or maybe you're gaming, and suddenly the bottom of the laptop gets uncomfortably warm. Or you unplug your phone charger and the brick is hot. What is physically happening there?
It's just the cost of doing business with electrons. Whenever you push electrical current through a circuit, whether it's a tiny transistor in a CPU or a big coil in an electric motor, you get resistance. And that resistance, it manifests as heat, and that heat is the enemy.
Right, because electronics operate best within a very, very specific temperature window.
Exactly. If a semiconductor gets too hot, its properties change. It gets unstable. If it gets really hot, it literally melts or burns out. So the heat sink's job is thermal management. It's a waste management system for energy.
The Eleanor Industries data breaks this down into a three-step principle that I found really helpful for visualizing this. It's not just cooling. It's conduct, transfer, and dissipate.
It's a great framework. Let's break that down. So, step one is conduct. This is the handshake. You have your heat source. Let's say it's the processor chip in your computer. That chip is generating intense heat at a microscopic point. The heat sink has to be in perfect physical contact with it to conduct the heat out of the silicon and into the metal.
And this is where it gets tricky, right? Because if that surface isn't perfectly flat, you get tiny air gaps.
And air is a terrible conductor of heat. It's an insulator. So if your heat sink base is even slightly rough or warped, the heat stays trapped in the chip, and the chip either slows down or it just fails. Step one is all about that interface.
Okay, so we've grabbed the heat. It's in the metal now. Step two is transfer.
Right. Now you have this hot spot on the base of the heat sink. You need to move that thermal energy across the rest of the structure as fast as possible. You want the heat to just race away from the source and spread out into the fins.
Which leads right to step three.
Yeah.
Dissipate. And this is where the shape of the thing becomes the star of the show.
Exactly. The goal here is to dump all that heat into the surrounding air. And the rate at which you can do that is determined almost entirely by surface area. You want as much metal skin touching the air as you can possibly get. That's why heat sinks look the way they do. All those ridges and fins and pins, they're just trying to maximize surface area in a really confined space.
It reminds me of biology. Like how our lungs are folded up inside our chests to create this massive surface area for oxygen exchange. The heat sink is basically the lungs of the computer.
That is a perfect analogy. You're trying to maximize the interaction between the solid metal and the fluid air.
So that brings us to the material. We've established we need something that conducts heat well and can be shaped into these complex lung-like structures. The title of the episode is Aluminium Heat Sink Profiles. But looking at the periodic table, isn't copper a better conductor?
It is, yeah, significantly better. If you look at thermal conductivity numbers, copper is roughly twice as efficient as aluminium at moving heat.
So why aren't all our laptops made of copper? Is it just the price? I know copper is expensive.
Price is definitely a factor. Copper is a semi-precious metal in industrial terms. But it's not the only reason, not by a long shot. Aluminium hits this perfect sweet spot across 5 different categories that just makes it the industry standard.
Okay, let's walk through those because I think it explains a lot about modern device design.
First, as we said, is thermal conductivity. Aluminium isn't the best, but it is excellent. For, 95% of applications, it's more than fast enough to get the heat away from the source. It's the good enough threshold.
Right. You don't need a Ferrari just to drive to the grocery store.
Exactly. Second is weight. And this is the absolute killer for copper. Copper is incredibly dense. If you replace the aluminum heatsink in a modern laptop with a copper one of the same size, that laptop would be uncomfortably heavy. In aerospace or automotive applications, that weight penalty is just unacceptable. Aluminum gives you great cooling performance at a fraction of the weight.
That makes perfect sense,
It's
especially in electric vehicles where range is everything. You don't want to be hauling dead weight.
Precisely. Third is corrosion resistance. And this is fascinating from a materials science perspective. Aluminium has a natural affinity for oxygen. So as soon as it's exposed to air, it forms this microscopic layer of aluminium oxide on the surface.
So it rusts immediately. Or wait, not rust. It reacts.
It reacts immediately, yeah. But unlike iron rust, which flakes off and eats away at the metal, aluminium oxide is like a ceramic shell. It's incredibly hard, and it seals the metal underneath from any further corrosion. So you can put an aluminium heatsink in a damp streetlight or a humid server room, and it just protects itself.
And the source material mentions you can enhance that with something called anodizing.
Yes. Anodizing essentially thickens that protective layer artificially, but, and here's a cool detail, anodizing also improves emissivity.
Okay, break that down for us. What is emissivity?
It's the ability of a surface to radiate heat as infrared energy. A shiny, polished surface is actually terrible at radiating heat. It just holds it in. A matte, anodized surface is much, much better at radiating that energy away. So anodizing doesn't just make it look cool. It actually helps the physics of step 3, dissipation.
That is a very cool detail. Okay, so we've got conductivity, weight, corrosion. What are the last two?
Number 4 is cost effectiveness. Not just the raw material, but the processing cost. Aluminium is abundant and it's easy to work with, and that leads directly to number 5, design flexibility. Specifically, how well aluminium works with a process called extrusion.
Okay, yes. Let's get into the manufacturing, the how it's made part. The Eleanor Industries documents focus heavily on extrusion. I think most people have this vague idea of it, like that Play-Doh factory toy where you squeeze the star shape out.
That's exactly the principle. But just imagine doing it with solid metal and hundreds of tons of pressure.
So walk us through the journey. It starts as a big log of aluminium.
Essentially, yes. You have a billet, which is a solid cylinder of aluminium alloy. Step 1 is heating. You heat this log up to about 500 degrees Celsius. It doesn't melt. It's not liquid soup. It just becomes plastic. Think of it like stiff clay or warm taffy.
So it's soft enough to move, but still solid enough to hold a shape.
Right. Then comes the push. A massive hydraulic ram pushes this softened billet towards a steel die. The die is a thick steel disc with a profile shape cut into it. All the fins, the ridges, every complex detail.
And the aluminium is forced through those tiny openings.
It just flows right through them. It's incredible to watch. You have this massive log going in one side, and on the other, out comes this long, continuous strip of complex, finned metal. That's the shaping phase. It lets you create these incredibly intricate surface areas in just a single pass.
And because it's continuous, I assume you just chop it to whatever length you need.
Exactly. After it comes out, it goes through cooling, usually air or water quenching, to lock in the metal structure, and then straightening because it can twist a bit. And then they just saw it to length. So if you need a 1-inch heatsink for a router or a 6-foot one for a solar inverter, it can come from the same extrusion run.
It seems incredibly efficient. But the source material lists a few other types. It sounds like extrusion has its limits.
It does. Extrusion has what we call an aspect ratio limit. You can't make the fins too tall and too thin, or they'll just snap off inside the die. If you need really, really dense fins, you use a process called skeeving.
Skeeving. That sounds like something you do in a deli.
It's actually very similar to slicing meat, but with a twist. You take a solid block of aluminium. A machine uses a precise blade to slice a thin layer off the top of the block. But, and here's the key, it doesn't slice it all the way off. It slices it and then bends it upward into a vertical position.
Wait, so the fin is still attached at the base. It's carved from the same piece of metal.
Exactly. And that is the magic of skeeving. Because the fin is part of the base material, there's no joint, No glue, no solder, no gap. That means there's zero thermal resistance between the base and the fin. It's a perfect connection.
And I imagine you can pack those fins really, really close together that way.
Extremely close, much closer than you can with extrusion. So if you have a tiny space like inside a compact server or a high-performance laptop and you need massive surface area, skeeving is the answer.
That's fascinating. Okay, what about when you need to go really big? The notes mention bonded fin heat sinks.
That's the other end of the spectrum. Let's say you need fins that are 4 or 5 inches tall to cool a giant industrial motor. You can't extrude that, and you certainly can't skeeve it. So you make the base separately, and you make the fins separately. Then you bond them together.
Bond them how? With glue.
Sometimes a specialized thermal epoxy, but more often it's brazing or soldering. You cut grooves in the base, you slot the fins in, and you bond them. It allows for these massive cooling towers that would be impossible to make as a single piece.
And then, for the absolute top-tier mission-critical stuff, there's CNC machining.
That's subtractive manufacturing. You take a solid block and you just carve away everything that isn't the heatsink. This is for when you need really complex 3D shapes, curves, weird angles, special mounting points. It's slow, it's expensive, so you see it in aerospace, medical devices, that kind of thing.
The research also mentioned something called advanced geometries, specifically cross-cut patterns. Why would you cut across the fins? I thought you wanted smooth channels for air to flow through.
Usually, yes. But if the air channel is too long, the air right next to the fin can get stale. A layer of hot air forms. It's called the boundary layer, and it just sits there. It acts like a blanket, trapping the heat in.
So the fresh, cool air just glides over the top of this hot air layer.
Exactly. By cross-cutting the fins, turning them into a grid of pins, essentially, you create turbulence. Now, turbulence is chaotic, but in cooling, chaos can be good. It breaks up that boundary layer and forces fresh air to mix right against the hot surface. It scrubs the heat away more effectively.
So it's active mixing, but with no moving parts.
Precisely.
Let's shift gears to where these things actually live. We talked about laptops, but the application list from Eleanor Industries is huge. One that stood out to me was LED lighting. I always think of LEDs as the cool light source. And you can touch an LED bulb, and it doesn't burn you like the old ones.
That's a really common misconception. The light beam itself is cool, yes. But the electronics driving the LED and the tiny chip itself, they generate a massive amount of concentrated heat.
And what happens if you don't cool it? Does the bulb just pop?
It's more subtle. You get something called lumen degradation. As the LED chip overheats, the chemical structure of the phosphor starts to break down. The light doesn't just go out, it gets dimmer and dimmer, and the color shifts. It starts to turn this weird blue or green.
So when I see those street lights that look really dim or have that odd color,
Yeah.
that's a heatsink failure.
Very likely, yes. Or just a poor thermal design from the start. For a street light to last 50,000 hours, the heat sink on the back has to keep that little chip at a steady temperature through freezing winters and scorching summers.
That brings us to renewable energy. I have to admit, I hadn't connected heat sinks to solar power before.
Oh, it's absolutely critical. Think about a solar inverter. Its job is to take the DC power from your panels and switch it into AC power for your house. It's doing that switching thousands of times a second. Every single switch generates a tiny spark of heat. Multiply that by kilowatts of power, and you basically have a furnace.
And efficiency is the name of the game in solar.
It's everything. If that inverter gets too hot, its electrical resistance goes up. You literally lose energy as heat. You are harvesting less sun because your equipment is too hot. So those cooling fins on the side of your inverter are directly tied to your energy bill.
And batteries. We hear so much about thermal management in EVs.
Batteries are like Goldilocks. They hate being too cold, and they really hate being too hot. If an EV battery gets too hot during rapid charging or hard acceleration, it permanently degrades. You lose capacity forever, or worst case, you get thermal runaway. Fire.
So the heatsink in an EV isn't just about performance, it's a core safety device.
It's the primary safety barrier, and the motor controllers are the same. When you stomp on the accelerator of a Tesla, you're dumping hundreds of amps into the motor. That creates this huge vertical spike of heat in the controller. The heatsink has to absorb that spike instantly to keep the electronics from frying.
So, knowing all this complexity, let's say an engineer is listening and designing a new device. The source material has a section on strategic selection. It sounds like you can't just buy a generic heatsink off the shelf.
Not for anything serious, no. It's a very specialized supply chain. You really need to vet your manufacturer.
What are the big green flags to look for, or red flags?
First, look at their extrusion capabilities. Do they have the right press tonnage? If you have a complex design with really thin fins, a weak press just can't push the metal through the die properly. You get wavy fins or inconsistent walls.
And then there's CNC accuracy. We talked about how important that flat base is.
This is huge. We call it flatness tolerance. You need a manufacturer that can machine that base to be flat within microns. If they're sloppy and the base is even slightly concave, you get an air pocket right over your CPU. And that's a catastrophic failure just waiting to happen.
What about certifications? The notes list ISO 9001 and ISO 14001. Are those just, resume padding?
In manufacturing, they're really important indicators of process control. ISO 9001 means they have a system to ensure consistency. So heatsink number 1 and heatsink number 10,000 are identical. ISO 14001 is environmental management, which really matters because making aluminium is energy intensive. You want a partner who manages that impact responsibly.
And finally, customization.
This is just the reality of modern design. Off-the-shelf parts are great for prototypes, but if you're building a sleek new smartphone or a specialized medical device, you don't have a simple square box to work with. You need a custom shape, a custom alloy, custom mounting brackets. You need a manufacturer who acts as a design partner, not just a vendor.
It really changes your perspective. I mean, we started this talking about a hot laptop, but when you zoom out, you realize that thermal management is the hidden backbone of the entire grid.
It brings us right back to that idea of the thermal wall. We often think of technology being limited by smarts. Can we write the code? Can we design the chip? But more and more, we're being limited by pure physics. Can we get the heat out fast enough?
That's a sobering thought. The limit of our AI, our electric cars, our renewable energy grid, it all comes down to how water we can move heat from point A to point B.
Exactly. We demand infinite power, but nature demands we pay for it with heat. The aluminum heatsink is the only thing balancing that ledger.
So the next time your phone gets warm in your hand or you hear a fan spin up, don't just get annoyed. Remember that there's a piece of precision-engineered aluminum in there, furiously conducting, transferring, and dissipating that energy so you can keep on scrolling.
No moving parts, no electricity, just pure physics working for you.
That's a wrap for this deep dive into the world of aluminum heatsink profiles. A big thank you to the insights from Eleanor Industries for helping us decode the metal. And thanks for listening.
Stay cool, everyone.
We'll catch you on the next one.